In the previous video, I talked about the SVM's main idea, and just as a recall, this idea was to maximize the margin. This is the first thing, and then we need to get the decision boundary in between or in the middle of this margin. So this is an example of a margin, and it should pass from at least one sample, right? And inside of this margin we shouldn't have any sample, so no sample should be inside of this margin here, right? So what we are trying to do is first to maximize the width, so I will denote this width as d, right? So we want to maximize d such that there is no sample inside of that margin, of course, because if we maximize d like that, for example, then I would have many samples inside of that margin. So this is not what we want. We have a constraint here. And of course, the second goal is also to find the line that passes from the middle, or the decision boundary that should pass from the middle of this boundary, and I also explained why in the previous video. So this is my decision boundary. Should be like that. Okay, now if I want to maximize d, theoretically I need, of course, to find an expression for d and then work out an optimization problem. Well, what is the start? What is step one? Well, step one is to start from our decision rule or decision function, which is written in this form. So this was our decision rule. So w when dotted with xi plus b should be higher than 0. If it is higher than 0, then the class, or xi, belongs to the positive class. This is p. This is the positive class on this side, and this is the negative class on this side. Otherwise, if it's smaller than 0, then xi belongs to the class n, right? This was my decision rule. Okay, so now what should we do? First of all, before going to the second step, I just need to make sure that we understand what's the meaning of this expression. What does this expression? Well, this expression just gives me a distance, or a measure of distance, from this decision line here. So, for example, if I have a point here, then I will get a positive value, and this positive value is just a measure of the distance between this point here and the decision boundary. Similarly, if I have a point on this side, I will get a negative value, but the absolute value of this negative value represents, or is a measure of distance between this point and the decision boundary. Now, why I'm talking about the measure, why I'm not saying it's exactly the distance? Well, it's exactly the distance only if the magnitude of w is equal to 1, right? So if this is true, then this thing here represents the distance. Okay, so now this is what I will do. I will assume that w is 1, and I will try to change my decision rule. I will try to change this. Now if I observe my graph here, I can immediately see that all my positive samples are at least this far from the decision boundary, and this is just d by 2. Also, all the negative samples are this far, or are at least this far from this decision boundary, which is d by 2. And d, by the way, is the width of the margin that I want to maximize. Okay, so now what's the modification I should do? I think it's obvious. I could say that w dotted with xi plus b, this should be if this is higher than plus d by 2, then I could say that the training sample, or the 8th training sample, belongs to the class P. Okay, and I can say higher or equal. Otherwise, if it's smaller or equal than minus d by 2, then the 8th training sample belongs to the class N. This is the new modification I have for my decision rule, and there is no problem in doing that, because by observing the graph we can see that this is true. Now what we need to know is that W, or the magnitude of W, is not always 1, because remember, this is true, this thing here is true only if the magnitude of W is equal to 1. And W, just a reminder, W is a vector that points perpendicularly to the decision boundary. This is my decision boundary. This is W, just in case you forgot about W. Okay? So now, what I want to do is to normalize against the magnitude of W. So I want to make this decision rule valid no matter what the value or the magnitude of W. So in that case, what I need to do is just to divide this thing here by the magnitude of W, and it would be correct. So this is the modification I need to do. I just need to divide this by the magnitude of W, right? And then it would be correct no matter the magnitude of W. So the magnitude of W in this case does not matter, so it's not necessarily 1. I can just get rid of this assumption. So just let me write this again here for this condition 2. And I should divide by the magnitude of W, and when I divide by the magnitude of W, this thing here gives me the distance, exactly the distance from the decision boundary. And this distance is negative if I'm on this side of the boundary. Now, what's the meaning of this? Now I got to this equation, or to this point. What I can do first, I will move this W from this side to this side of this equation, and I will do the same for this W here. I will remove it from this side to this side, right? So I can write this. I can say W W dotted with xi plus b is higher or equal than the magnitude of W multiplied by d by 2. Similarly here, I could say for the second, in this case, xi belongs to positive class. Otherwise, if this decision rule is smaller or equal than minus W multiplied by d by 2, in that case xi belongs to the negative class. So this was my original decision rule. If you remember, this is my original decision rule, d of x. And now we need to, try to interpret that. Now, what is the important interpretation in our case? Well, I can see here that the magnitude of W does not matter. What we are trying to find is the direction of W that would maximize this distance. If the magnitude of W changes, then this threshold here changes automatically according to the magnitude of W. For example, if W is equal to 1, then I would have here as a threshold just d by 2. But if W is equal to 2, then this threshold here changes automatically, so to counter the effect of the magnitude of W, so as a threshold here I would have only d if w is equal to 2, right? So now, why this is important in our case? Well, it's important because I can set w equal to d by 2. So this is an arbitrary choice, and I have right to do that because, as I said earlier, the magnitude of w does not matter, right? And since the magnitude of w does not matter, then I can make it anything I want, and I choose it to be equal to d by 2. Now, if you don't see it yet, I have already found the expression of the width of the margin, which is this thing here. So d, this is d, is equal to I made a mistake here. So my arbitrary choice should be this, should be w equal to 2 by d, okay, to 2 by d, because if I do that and I replace w here, I would get this side here equal to 1. This is why I took this this arbitrary choice. So w is equal to 2 by d, and this means that the width of the margin is equal to 2 divided by the magnitude of w. So this is the expression of the width of the margin. So now I can see that if the w increases, then d decreases, whereas if w decreases, then d increases. But the thing here is, I need to take into account this constraint here. Remember, my goal is not only to maximize the margin, this d here, the width, is not only to maximize the margin, but I need to maximize the margin such that there is no sample, no training sample inside of that margin. In other words, this translates mathematically into this equation, into this constraint here. So this is the constraint. So my optimization problem now is to maximize the width of the margin, which is 2 by w, while taking into account this constraint. Now, in this constraint here, I have two equations, or two conditions, and what I will do is just to simplify these two conditions into one equation. I will simplify these two equations into one equation by introducing a new variable called yi. This is what I will do. I will say, I will consider a new variable yi, such that, of course, I is associated with the 8th training sample, right? So I want to make yi equal to 1 if xi belongs to the positive class, and minus 1 if xi belongs to the negative class. And I can do this because I know the class of all my training samples, right? All the training samples have a known class, therefore I can find yi that would satisfy these two values here. Now, based on that, I can modify this equation here by multiplying everything here by yi. So this is what I will get. I will get yi multiplied by w, multiplied by this thing here, by this term, which is w dotted with xi plus b, and this thing should be higher or equal than w multiplied by d by 2. So what is w? What is d? D is equal to 2 by w, so this thing here becomes 1. So I will get here 1. Okay? So that's it. I have now two constraints or two equations into one equation. And if you want to check this out again, you can just replace yi and see what would happen. If the sample is positive, you just replace yi here, then you would get w dotted with xi plus b higher than 1. This is positive sample. If the sample is negative, then you just replace this thing here by -1, so you get -1 multiplied by w dotted with xi plus b, and this is higher than 1. You just bring this -1 here, so you get w xi plus b smaller or equal than -1. Right? We have two equations that are the same as these two equations here.